Hello and welcome. In this video, we are going to deconstruct the mechanics behind the latest breakthrough in AI, the working of reasoning models. To understand them, we first need to look at the standard large language models we've used for years. Think of a standard LLM as a highly efficient pattern matcher. When you ask it a question, it generates an answer almost instantly, token by token, in a linear path. It's essentially speaking as it thinks, like a reflex. Reasoning models, however, operate differently. They introduce a deliberate latency, a pause, before they respond. During this pause, the model isn't idling. It is engaging in a chain of thought. It is planning out steps, verifying its own logic, and even backtracking to correct errors. This shift from rapid pattern matching to deliberate structured thinking is what allows these models to solve complex problems that stump standard AI. To appreciate the innovation of reasoning models, we must first establish a baseline. How does a standard large language model operate? Let's say we give a standard model this simple prompt. It doesn't know the answer in the way a human does. Instead, it treats this as a statistical completion task. Internally, the model calculates a probability distribution over its entire vocabulary. It asks, based on the words seen so far, what token is most likely to come next? Here, the statistical association between France and Paris is incredibly strong, giving it the highest score. The model identifies this winner and commits it to the sequence immediately. This is the essence of next token prediction. It is fast, effective for retrieval, and linear. Information flows in one direction, from input to calculation to output, without pausing to plan or verify its own logic. But what happens when the problem is too complex for a single, straight-shot guess? That is where reasoning models change the game. To truly appreciate how reasoning models differ, we must first understand the baseline, how standard large language models, and indeed a part of our own brains, operate. Psychologists, most notably Daniel Kahneman, refer to this as System 1 thinking. System 1 is fast, intuitive, and automatic. It doesn't pause to ponder, it simply reacts. Let's look at a few examples. If I ask you, what is 2 plus 2? You didn't calculate that. You didn't count on your fingers. The answer 4 just appeared in your mind. It was a memory retrieval, a pattern match. Standard language models operate almost exclusively in this mode. If you ask a model for the color of the sky, it predicts blue instantly. It's not simulating the atmosphere's physics. It's recalling a statistical association from its training data. This applies to language patterns too. Start the phrase, actions speak, and the model completes it louder than words. This is next token prediction. For these tasks, System 1 is efficient and accurate, but because it relies on intuition rather than deliberation, it lacks the ability to stop and check its work. To understand why we need reasoning models, we first need to see where standard large language models fall short. Let's look at a classic transentity problem. We have three simple statements. A is older than B. B is older than C. The question is A older than C? When a standard LLM processes this, it operates as a linear predictor. It reads the text and it rushes straight to the answer based on surface level probability. It sees a pattern of comparison and predicts the next likely token, yes. And in this case, the answer is correct. But look closely at the path it took. Notice this empty space? This is the logic gap. The model went directly from premise to conclusion without constructing the intermediate link. It didn't explicitly verify that if A is greater than B and B is greater than C, then A must be greater than C. It just guessed the pattern. For simple text, this works. But for complex problems, this linear guessing leads to hallucinations. The model provides a confident answer without ever actually doing the math. To fix this, we need to fill this gap with actual thinking. To understand why reasoning models are necessary, let's first look at the fatal flaw of standard models, the hallucination cascade. Consider a standard chain of thought process attempting this math problem. The model begins by calculating 12 plus 19. Here is the critical moment. The model makes a minor arithmetic error, outputting 30 instead of 31. It's a small slip, but watch what happens next. Because standard models are autoregressive, they treat everything they have generated so far as absolute reality. This error doesn't just sit there, it propagates. Now, the model moves to step 2. It takes that incorrect 30 and uses it as the foundation for the next logical step. Notice that 30 times 2 is 60. The logic within this step is perfectly valid. But the premise was flawed. The model continues confidently down this path of reasoning, unaware that it has drifted away from the correct solution. It calculates 60 minus 5, arriving at 55. The model is confident, and its internal logic is consistent. But because it lacks the ability to look back and self-correct that initial slip, the final result is completely wrong. This is the limitation reasoning models aim to solve. To understand how reasoning models differ from standard AI, we need to introduce a concept from cognitive psychology, the distinction between System 1 and System 2 thinking. Standard language models primarily operate on System 1. They are fast, intuitive, and reactive, generating the next token almost instantly based on surface-level patterns. Reasoning models, however, are designed to unlock System 2. This is the slow, analytical mode of thought. The defining characteristic of this mode is visually very simple, a pause. Instead of immediately rushing to output an answer, the model explicitly holds the generation process. It takes time, sometimes seconds, sometimes much longer, to perform inference time compute. But what is happening during the silence? First, the process is deliberative. The model isn't just guessing, it is weighing different options and considering the context deeply. Second, it is logical. It attempts to construct a valid chain of reasoning, ensuring that step B actually follows from step A, rather than just sounding like it does. And finally, it is planned. Unlike a standard model that writes linearly without looking ahead, a reasoning model maps out a path to the solution before committing to a final answer. This thinking time is the crucial architectural shift that allows AI to move from fluid mimicry to reliable problem solving. To understand how these models achieve high performance, we need to look at what happens between the prompt and the response. Let's say we ask the model to write a haiku about logic. A standard model might try to predict the entire poem at once, but a reasoning model does something different. It opens a hidden scratchpad, a sequence of tokens invisible to the user, known as the chain of thought. Here, the model effectively talks to itself. It analyzes the constraints, identifying the 575 syllable structure first. Then it plans its content, selecting keywords like code and flow before it even commits to a final verse. It can even critique its own draft tokens. This intermediate computation allows the model to catch errors and structure its thinking linearly, just like a human working out a problem on paper. Only after this internal process is complete does the model generate the final answer you see on your screen. By separating the reasoning process from the final output, the model trades speed for accuracy, ensuring the result actually follows the rules. To understand why reasoning models are different, we have to change how we look at text generation. In this paradigm, generating more tokens is literally equivalent to doing more computation. Text generation is the thinking process. Let's look at a standard model. When you ask a standard model a question, it aims for the answer immediately. It spends very little compute time, roughly 1 second here, rushing to the finish line. It relies on instinct. But a reasoning model takes a different approach. It buys itself time to think. Instead of answering, it starts generating thought tokens. Here, it might be planning its approach. Then it spends tokens verifying its own logic or catching errors. And finally, it synthesizes the answer. This generates far more tokens, taking 10 seconds instead of 1. This extra length isn't inefficiency. It is the model buying intelligence with time. By expanding the context window with these intermediate steps, it allows the computation to go deeper, solving problems that instantaneous instinct simply can't handle. Building on the concept of the hidden state, let's see a concrete example of a specific reasoning pattern, decomposition. Consider a classic estimation challenge, often called a Fermi problem. How many golf balls fit in a Boeing 747? A standard language model might immediately attempt to predict a number based on training data, often hallucinating a plausible sounding but incorrect answer. However, a reasoning model uses its hidden state to pause and break the problem down. It essentially asks itself, first, I need to determine the internal volume of the aircraft. Next, I must define the volume of a standard golf ball. And crucially, I need to account for packing efficiency, the empty space between spheres. By explicitly decomposing the goal into these manageable intermediate steps, the model transforms a vague estimation task into a series of solvable math problems. This structured thinking occurs entirely within the hidden state tokens we discussed earlier, before the final answer is ever generated. To understand how this works, let's visualize the model's mind not as a straight line, but as a branching structure. It starts with the problem, but instead of immediately shouting out the first word that comes to probability, it generates multiple possible approaches. In research, we call this the tree of thoughts. Let's say the model decides to simulate plan A. It takes a reasoning step, projecting what happens next. Crucially, reasoning models have a self-evaluation mechanism. It looks at this step and realizes this logic doesn't hold up. This is a dead end. In a standard model, it might have hallucinated an answer here, but a reasoning model backtracks. It discards that thought and returns to the root. Now, it explores plan B. It takes a step, verifies its logic is sound, and continues deducing until it reaches a confident conclusion. Only after validating this entire chain does it present the final answer to you. By exploring, self-correcting, and verifying, the model trades a little bit of time for a massive increase in reliability. Moving deeper into the reasoning process, let's look at the crucial mechanism of self-correction. Suppose the model generates a candidate step, like x equals 5. In a standard model, this might be the final output, but a reasoning model treats this merely as a draft. It activates a verifier, an internal critique process. It asks specific questions against the prompt's rules. Is X positive? Yes, that checks out. But does it satisfy the boundary constraint? No. The verifier detects a conflict. Instead of hallucinating a justification, the model explicitly rejects this path. It backtracks and regenerates the step with the constraint in mind, arriving at x equals 7. This critique and refine loop is why reasoning models are far more reliable for complex math and logic. To understand why this capability is so revolutionary, let's compare the architecture directly. On the left, we have the standard model we're all familiar with. It operates like a reflex. Input comes in, it passes through the layers linearly, and the output is generated immediately based on probability. It's fast, but it's a one-shot attempt. Now, look at the reasoning model on the right. The architecture introduces a critical new component, a feedback cycle. When a complex query arrives, the standard model rushes to the finish line, but the reasoning model stops. It enters a thinking phase. Inside this loop, the model isn't just generating text, it is generating thoughts. It plans a solution, verifies its own logic, and even backtracks if it spots an error. Only after this internal deliberation is complete does it commit to the final answer. We call this invisible loop the chain of thought. It trades speed for accuracy, effectively allowing the model to think before it speaks. To understand reasoning models, we first need to look at how we traditionally train them using outcome-reward models, or ORMs. Think of a complex reasoning problem like a maze. The model, like a mouse, needs to navigate from the start to the solution at the very end. In a traditional setup, the model makes a series of decisions, step by step. But here's the catch. If it makes a wrong turn halfway through and fails to reach the goal, it receives an outcome of 0. Crucially, it gets no specific feedback on which turn was the mistake. The entire effort is simply marked as a failure. The model only receives a positive signal if it navigates the entire chain perfectly, getting every single step right all the way to the solution. Only then does it get a reward of 1. We call this sparse reward because the feedback is only given at the very end. It's incredibly difficult for the model to learn how to think, as it's essentially fumbling in the dark until it luckily stumbles upon the complete solution. Building on the maze analogy, let's look at how modern reasoning models are trained using process reward models, or PRMs. Unlike the previous approach that only graded the final result, a PRM acts like a teacher, checking your work line by line. As the model solves the problem, it receives feedback at every critical reasoning step. Did it analyze the first part of the prompt correctly? Yes. This positive reinforcement tells the model it's on the right track immediately, rather than leaving it in the dark until the end. By validating each logical link in the chain, we ensure that the final answer isn't just a lucky guess, but the result of a sound, verified thought process. This method, known as step-by-step verification, drastically reduces logic errors in complex tasks. To operationalize this, we wrap our reasoning model in a reinforcement learning framework. Let's visualize this training loop. We start with our policy model, the neural network responsible for generating text. When presented with a problem, the model doesn't just guess an answer. Instead, it generates a thought trace, a step-by-step reasoning path, explicitly planning and executing its logic. Here is the critical difference. We don't just wait for the end. A reward model, or in some cases, human annotators, reviews this specific chain of thought and assigns a reward score. This score, let's say 0.9, quantifies how sound the reasoning was, not just if the answer was correct. This score becomes the signal for our learning algorithm. We calculate a gradient update, mathematically nudging the model's parameters, theta. This update flows back into the policy, slightly adjusting its neural pathways. The goal is simple: make the model slightly more likely to generate high-quality thoughts like the one we just scored, and less likely to hallucinate. This forms a continuous cycle. Iterate this process millions of times, and you don't just get a model that memorizes answers, you get a model that has learned the habit of structured thinking.
Building on the internal mechanisms we just explored, this leads to a profound shift in how we utilize these models. Inference time compute scaling. Let's visualize this. On a horizontal axis, we have thinking time, the computational effort spent after the prompt is received. On the vertical axis, we have accuracy. Standard models have a fixed performance, but reasoning models exhibit a different behavior. They follow a scaling curve where spending more compute during inference actually unlocks higher intelligence. Notice that as the model thinks longer, generating those intermediate plans, verifying steps, and self-correcting, it climbs this curve. It is effectively trading time for accuracy, while the returns are logarithmic. This capability means that for complex, non-trivial problems, simply allowing the model to ponder can be the difference between failure and success. This breaks the old paradigm where a model's intelligence was frozen the moment training finished.
Let's look at a concrete example: writing code. Suppose we ask a model to write a Python script to scrape a specific website. A standard language model acts on impulse. It immediately spits out the most probable tokens. It looks like valid code, right? But because it didn't plan ahead, it often forgets edge cases. It creates a script that crashes the moment the internet flickers, lacking necessary error handling. It prioritized speed over structure. Now, observe the reasoning model. When we give it the same prompt, it doesn't write a single line of code yet. It starts a hidden chain of thought. First, it identifies the right libraries. Next, it explicitly reasons that network requests can fail, deciding it needs a try-except block. Finally, it outlines the logic flow before committing to syntax. Only after this internal verification does it generate the output. The result isn't just syntax, it's a robust solution derived from a structured plan. While it took a few seconds longer, the reasoning process eliminated the bugs that the standard model blindly hallucinated. Let's look at a concrete example: a simple geometry problem. Here we have a triangle with sides 3, 4, and 5. We want to calculate the area. A reasoning model begins by explicitly stating the givens and verifying the properties, confirming it is indeed a right-angle triangle. Now, watch closely. In its thought process, the model might propose a calculation: base times height. A standard model might output this result immediately: 12. It looks plausible, but it's mathematically wrong. It missed the 1/2. But a reasoning model doesn't stop there. It runs a verification step. It detects that the formula used contradicts the definition of a triangle's area. It flags this path as invalid. It then backtracks, it discards the erroneous thought and generates the correct derivation, 1/2 base times height, giving us 6. This ability to draft, verify, and self-correct is what makes these models far more reliable for complex logic. Now, let's move to one of the most vital applications of this technology, safety and alignment. In standard models, safety is often handled by simple pattern matching, but reasoning models introduce a safety monitor directly into the thought process. Imagine a user submits a harmful request, like this. A standard model might rush to answer, but here, the model pauses to think. First, it explicitly analyzes the user's intent. It asks, what is this user actually trying to do? It recognizes the harm. Next, it consults its internal safety guidelines. It flags the request as a violation of its core policies. Finally, instead of generating dangerous instructions, it plans a refusal strategy. It decides to politely decline. Only after this robust internal check does it generate the final response. By using chain of thought to reason through safety rules step by step, the model becomes much harder to trick, ensuring that its outputs remain helpful, harmless, and honest. You've probably seen the viral trick where AI models fail to count how many R's are in the word strawberry. Why does a supercomputer fail at counting to 3? Let's look at the standard model on the left. To an LLM, text isn't a sequence of letters. It sees tokens, chunks of text. The word strawberry is often split into 2 tokens, straw and berry. The model processes these opaque chunks, not the letters inside them. It makes a probabilistic guess based on the token pattern and often gets it wrong. Now, let's look at a reasoning model. When asked this question, it doesn't just guess the next word. It initiates a thinking process. It explicitly breaks the word down into characters and iterates through them, verifying each one. It essentially says to itself, let's count. Here is 1, here is 2, and here is 3. By allocating compute time to verify the data step by step, reasoning models can solve precise logical tasks that standard models hallucinate. However, in engineering, there is no such thing as a free lunch. While the chain of thought offers incredible power, it introduces a fundamental trade-off. On one side, we have the massive benefit we just explored, reasoning accuracy. The model effectively thinks before it speaks, solving problems that stump standard models. But this thinking process, generating all those hidden intermediate thoughts, requires significantly more compute. This comes at a heavy price, high latency and high cost. Because the model generates thousands of token predictions just to plan its answer, it is much slower and more expensive to run. This means reasoning models are often not ideal for instant, real-time chat applications where speed is critical. However, running these massive reasoning models for every single query is computationally slow and expensive. We often want the speed and cost efficiency of a standard, smaller model. This brings us to a technique called distillation. Instead of training the small model on raw answers, we use the large teacher model to generate high-quality, step-by-step reasoning traces for complex problems. We then take these detailed thought processes and use them to train the smaller student model. The student doesn't just memorize the final output. It learns to mimic the process of reasoning. By absorbing these patterns, the small model upgrades its capabilities, becoming a distilled model. This gives us a powerful compromise, the sophisticated reasoning patterns of a giant model packed into a faster, cheaper architecture. Building on that internal chain of thought, state-of-the-art models like OpenAI's o1 are enabling a massive shift, the transition from chatbots to agents. At the center, we still have our reasoning model, but instead of just predicting text in a void, we now place it at the center of an ecosystem. We give it hands, access to the web, a code terminal, or a file system. The reasoning engine doesn't just talk anymore, it orchestrates. Consider a complex request. The model realizes it lacks data. It doesn't guess, it pauses generation, plans a search query, reaches out to the browser, and reads the result. Or perhaps it needs to solve a math problem. It writes a Python script, sends it to the terminal to execute, and captures the output. If the code fails, the reasoning model analyzes the error trace and self-corrects. This loop, planning, acting, and observing, is the engine of agency. By combining deep reasoning with external tools, the model graduates from a passive predictor to an autonomous agent. Let's consolidate everything we've learned into a single architectural view. It begins just like a standard model. The input is processed by the transformer core to create an initial embedding. But here is where the architecture diverges. Instead of immediately predicting the next word, the model enters a reasoning loop. Here, it iterates between generating potential steps, search, and verifying their validity. This cycle creates a thought process hidden from the user. Once the reasoning loop finds a high-confidence path, it doesn't just guess. It passes the result to a reward model, which acts as a final gatekeeper, ensuring the solution meets quality standards before delivering the final output. If we trace the flow of information, we see the time to think. The model spends the majority of its compute budget here in the loop, refining its logic until the solution is verified and finalized. This architecture trades inference speed for reliability and depth. Ultimately, the evolution we are witnessing is a shift in the very nature of generation. For years, standard large language models have operated on reflex. Like a lightning bolt, they map input to output in a single rapid pass, relying on probability to mimic intelligence. But reasoning models introduce a new dimension, deliberation. By spending compute time during inference, planning, verifying, and self-correcting, these models trade instant answers for accurate ones. They represent a move from AI that simply speaks to AI that truly thinks before it speaks.